Welcome to the lecture series of signals and systems. In the last lecture, we have seen some important examples related to the Laplace transform, and these examples can clear the picture of the use of ROC or utility of ROC in the determination of the Laplace transform of the signal. So, for the better clarification and better view of the ROC, of the Laplace transform, we will consider some more examples, and then we will go to the properties of the Laplace transform. So the task of the including some examples is to clarify the concept of the region of convergence, which is a special part included in the Laplace transform. So the given example here is, it is given that xt is equal to e power 2t, or I will write it e power minus 2t ut, e power minus 2t ut plus e power 3t u of t. Getting the Laplace transform of such type of functions is quite easy. It will directly become Laplace transform of e power minus 2t will become 1 upon s plus 2. The Laplace transform of e power 3t will become 1 upon s minus 3. As we seen earlier, the Laplace transform of e power 80. But we have to specify the region of convergence of this function if we are going to convert this function in the frequency domain by using Laplace transform. That is the important. So we know the expression to get the Laplace transform of the given signal. This is minus infinite to plus infinite xt e power minus st gt, or I will write it as, in place of xt, it is e power minus 2t ut plus e power plus 3t ut into e power minus st dt. This can be further simplified as, and we can distribute the integration inside the bracket as, this is minus infinite to plus infinite e power minus 2t ut e power minus st dt plus minus infinite to plus infinite e power 3t ut into e power minus st dt. Because ut is given here and ut is given here also, so this limit will become from 0 to infinite. That's why I will put limit here from 0 to infinite e power. Now this minus 2t and minus st will become minus s plus 2t dt, and this will become limit from 0 to infinite e power minus, if I will take t common here, minus t, this will become s minus 3t dt. Now what we have to do is simply integrate and get the result. So integration of this will become e power minus s plus 2t divided by minus s plus 2, and this integration will result in e power minus s minus 3 into t divided by minus s minus 3. Limit is from 0 to infinite on both the integrations. Now what we are doing all this to get the region of convergence of this equation. So this equation will converge if this value will be positive, because when I will put t equal to plus infinite here, this will become e equal to minus e power minus infinite. But if this term s plus 2 is negative, then this will become e power plus infinite, and that will not lead to the convergence. To converge the relation, it is needed that this term s plus 2 should be greater than 0. Here also, this term s minus 3 should be greater than 0 so that this summation can converge. So for the convergence, it is important that will these two values should be positive. So for the purpose of ROC, I will write here this s plus 2 should be greater than 0. It means that s should be greater than minus 2. And from here, this s minus 3 should also be greater than 0, or we can say that this s should be greater than 0. And further, I will find the value of this integration. This will become e power minus infinite, and e power minus infinite will become 0. So x of s will be equal to 0 minus, I will put t equal to 0 here, and when I will put t equal to 0 here, it will become e power 0, which is equal to 1 upon minus s plus 2. Similarly, this will become 0 minus 1 upon minus of s minus 3. And so the Laplace transform of this function will be equal to 1 upon s plus 2 plus 1 upon s minus 3. But region of convergence is important. Region of convergence, from here I can find that, from this relation I will find that value of the s should be greater than minus 2, means this region. And from this relation I will get that value of s should be greater than plus 3, means this region. It means that this integration will converge in this region, and this integration will converge in this region. If we combine both these two ROCs, this will become, because if s is greater than 3, it means that it will also be greater than minus 2. So the combined ROC of these two can be shown as it should be greater than plus 2. This is the ROC of the given Laplace transform e power minus 2t plus e power plus 3t ut. Now consider one more important case where xt is given as e power minus 80 ut minus e power minus bt u of minus 3. In the next example, xt is given as e power minus 80 u of t minus e power minus dt u of minus 2. We have to get the Laplace transform for this given function. So we can find the Laplace transform of this function very easily, but region of convergence is important. To get the region of convergence of the given function, we have to write some steps. We know that the Laplace transform can be written as integration from minus infinite to infinite x of t e power minus st d. The given function xt here is, in place of xt I will write e power minus 80 ut minus e power minus bt u of minus t into e power minus st. Again, distribute this integration in the given bracket. This will become limit from minus infinite to plus infinite e power minus at ut into e power minus st dt minus limit is from minus infinite to plus infinite e power minus bt u of minus t e power minus st, or we can write it as this ut will exist only from 0 to infinite. Before 0, value of ut is 0, so I will put limit here from 0 to infinite, and this will become e power minus s plus a into t. I will take minus t common from these two powers. It will become e power minus s plus a into t dt minus, now u of minus t is given here, means u of minus t will exist only for the negative values of t, only for the negative values of t. So in this integration, in this limit, I will consider only negative values of t, means from minus infinite to 0, and this will become e power minus of s plus b into t minus of s plus b into t dt. Now remaining it simple. We have to determine the value of this integration only, or further we can simplify one more step. This will become 0 to infinite e power minus of s plus a into t dt minus, I can replace the variable t with minus t. This will become plus, and this will also become 0 to infinite e power plus s plus b into t dt. We can simplify this in this way. I will replace this variable t by minus t. This dt will become minus dt, so minus minus will become plus. Here, when I will put minus t in place of t, this will become e power plus s plus b into t. So the remaining is, all we have to do is determine the value of this integration. This will become e power minus s plus a into t upon minus of s plus a. Limit is same from 0 to infinite, plus here it is e power s plus b into t divided by s plus b. Limit is same from 0 to infinite. This is what we will get from the relation of Laplace transform. Now we have to put the limit. When I will put upper limit here infinite, this will become 0, but this will become 0 only when, if the value of s plus a is positive. If it is greater than 0, means s should be greater than minus a. S should be greater than minus a, and this relation will converge only because it is e power plus s plus b into t. So if I will put infinite in place of t, this will become infinite. It means that the value of s plus b should be less than 0, because if the value of s plus b will be negative, then this will become e power minus infinite, and that will lead to 0. Now it means that this s should be less than minus b. Now relation more this when I will put t equal to infinite here, this will become 0. So x of s is equal to 0 minus when I will put t equal to 0 here, this will become 1 upon minus of s plus a plus because s plus b is negative here, so this will also become 0 plus 1 upon s plus b. Now we can write the Laplace transform of the given function as 1 upon s plus a plus 1 upon s plus b. This is the Laplace transform of given function, but ROC is important. In the first case, it says that the region of convergence of this transformation will be value of s which are greater than minus a. Values of s which are greater than minus a. Suppose minus a is here. So s should be greater than minus a means this region. I will plot in a wide area so that the picture of ROC will become clear. From here, the first case says that S should be greater than minus A. Suppose here is, suppose minus A is here in the given. Suppose minus A is here. So what it says that value of S should be greater than minus A means S should be in this region, in this sided region. S should lie in this sided region. And the second case says that S should be less than minus B. Suppose minus B is here, minus B is here. It means that S should be less than minus B, means this should S for the existence of this term, this S should exist to the left side of minus B. So after combining all these two ROCs, this will look like, means S should exist from minus A to minus B. S should exist from minus A to minus B. This region. In this region, both the conditions will be satisfied, that S should be greater than minus A and S should be less than minus B. Both these two conditions are satisfied only in this region if S is between minus A to minus B, means S should lie in the region, sided region here, where S is greater than minus A and less than minus B. So the Laplace transform of the given function will exist, but the condition is the convergence factor e power sigma, e power minus sigma, in the convergence factor sigma should lie in this region from minus A to minus B. And also the Laplace transform of the given system will exist only when the given values of A and B should follow this relation. Minus A should be greater than minus B, or we can say that B should be greater than A. If B is greater than A, or if B is greater than A, then obviously minus A will be greater than minus B, or because value of a here, value of a is greater than b, so I will write it as a should be greater than b or minus b should be less than minus b. So this will the Laplace transform will exist only when these two terms a and b, these two variables a and b will follow this relation that a should be greater than b. Only then the Laplace transform of this function will exist. So this is the important condition on the sigma, that it should lies between minus a and minus b. Only then we can find the Laplace transform of the given function e power minus at ut minus e power minus bt u of minus t. Now, so what we have seen, the ROC will exist only when minus a is greater than minus b. There are some more examples also, like the given one, which says that x of t is given as e power minus a mod of t. X of t is given as e power minus a into mod of t. And we know the definition of the modulus function, that mod of t will be equal to mod of t will be equal to plus t when t is greater than 0, and it will be equal to minus t when t is less than. So put the value of xt in the relation of Laplace transform, x of s will become equal to integration from minus infinite to plus infinite e power minus a mod of t e power minus st, or I will divide the limit in two regions. One is from 0 to infinite, another is from minus infinite to 0. So I will write it as minus infinite to 0 e power minus a mod of t into e power minus st dt plus 0 to infinite e power minus a mod of t e power minus st dt. Here the limit contains only negative values of t, and for the negative values of t, this mod of t will become minus t. So this e power minus at will become e power plus t. This is from minus infinite to 0, e power plus at e power minus st dt, plus in this range from 0 to infinite means for the positive values of t, this mod of t will become equal to plus t. So I will write it as e power plus at into e power minus st. Further, this can be written as minus infinite to 0 e power minus of s minus t dt plus 0 to infinite here e power minus of s plus at dt, or this can be simplified as e power minus of s minus a into t upon minus of s minus a. Limit is from 0 to infinite, plus it is e power minus of s plus a into t upon minus of s plus a. Limit here is, this is from minus infinite to 0, minus infinite to 0, and this is from 0 to infinite. Now, if I will put t equal to 0 here, this will become e power 0 means equal to 1. And when I will put this t equal to minus infinite here, this will become e power plus infinite because 1 minus is already here. What we want is this should become e power minus infinite. For that purpose, this value of s minus a, this value of s minus a should be negative. Should become negative means s minus a should be less than 0, or we can say that s should be less than a. And here, if I will put t equal to infinite, this will become e power minus infinite. But this will become e power minus infinite only when the value of s plus a is greater than 0. If s plus a will be positive, then after putting the t equal to infinite, this will become e power minus infinite. It means that s plus a should be greater than 0, means s should be greater than minus a, and put the limits after these considerations. Put the limit, this will become 1 e power 0 means 1 upon minus of s minus a minus e power infinite means 0 plus here it is e power infinite means 0 minus of 1 upon minus of s plus a minus of s plus a. So this will be written as 1 upon minus 1 upon s minus a plus 1 upon s plus a, or we can say that x of s will be equal to 1 upon s plus a minus 1 upon s minus a. Further, this can be simplified in two steps. This will become s minus a minus s minus a, s minus a minus s minus a upon s plus a into s minus a. This s and this s will get cancelled. This will become minus 2a upon s square minus a square. This is the Laplace transform of the given function e power minus a mod of t. Or also here is the first condition says that s should be less than a. Suppose a is a positive value, so suppose a is greater than 0, then a will lies somewhere on the right side of the s plane j omega axis. Here j omega and this is sigma, and minus a will exist to the left of minus j omega axis, left of j omega axis. And the condition says that s should be less than a, means s should lie in this region, s should lie in this region. And the second condition says that this condition says that s should lie to the right side of minus a, means s should be greater than minus a. So this will lie in this region. If we combine these two regions of convergence, the combined region of convergence will be in this region. This is the region of convergence lie between minus a and a. This is the region of convergence for the given function. It means that we can find the Laplace transform of the given function only when the sigma exists somewhere in this region from minus a to plus a. S sigma, or we can say that S should lie in this region which is covered by which is covered between minus a and plus a. That only when we can find the Laplace transform of the given function. So this is condition which is called region of convergence of the Laplace transform. Now consider some properties of the Laplace transform, some important property. Like in all the tools, there are some properties of the Laplace transform. Consider the first property as linearity. Linearity. Linearity says that if the Laplace transform of x1t is x1 of s and Laplace transform of x2 of t is capital X2 of s, then the Laplace transform of ax1t plus bx2t will result in a capital X1s plus b times capital X2s. This is what linearity property states. We can find the proof also. We can find the proof for the given property. Thus, it says that the x1t has Laplace transform equal to x1 of s, means x1 of s will be equal to x1t into e power minus st dt. Limit is from minus infinite to plus infinite. Also, x2s can be written as minus infinite to plus infinite x2 of t e power minus st dt. Then Laplace transform of ax1t plus bx2t can be written as integration from minus infinite to plus infinite ax1 of t plus bx2 of t into e power minus st dt. Or we can distribute the integration as Laplace transform of ax1t plus bx2t will be equal to minus infinite to plus infinite a times x1t into e power minus st dt plus b times integration from minus infinite to plus infinite x2 of t e power minus st dt, and compare these two results. x1s is equal to x1t into e power minus st, same as this, and expression for the x2s is same as this, x2t integration minus infinite to plus infinite x2t e power minus st dt. So in place of this function I will write x1 of s, and in place of this I can write x2 of s, and this will become equal to a x1 s plus b x2 s. This is what the linearity property of the Laplace transform states. The next property is shifting property. shifting property of Laplace transform. This property says that if the Laplace transform of x of t is capital X of s, then Laplace transform of x of t minus t naught will be equal to e power minus of s t naught x of s. Means if the Laplace transform of xt is known, then we can find out the Laplace transform of x of t minus t naught without any extra calculation. We have to simply multiply the s domain by e power minus st, and this will become Laplace transform of x of t minus t. So we can find the proof of this property as we know that the Laplace transform of xt can be written as minus infinite to plus infinite x of t e power minus st dt, which is equal to x of s. So what will be the Laplace transform of x of t minus t naught? This will be equal to minus infinite to plus infinite x of t minus t naught into e power minus st dt. Now replace this variable by some other variable. Suppose let t minus t naught is equal to some other variable z. So if t minus t naught is equal to some other variable z, then what will be limit on z? Limit on z, because when t will become equal to in plus infinite, then z will also become plus infinite. When t will become equal to minus infinite here, then z will also become minus infinite. So there is no change in the limit, and from here after differentiation we will get that dt will be equal to dz, and t will be equal to, now here t will be equal to z plus t naught. Substitute all these values in this integration. Laplace transform of x of t minus t naught will be equal to limit from minus infinite to plus infinite x of z e power minus s z plus t naught, z plus t naught into dz. Now this integration will be converted in this form, and this can be further simplified as integration from minus infinite to plus infinite x of z e power minus sz into e power minus st naught dz. And now, because we are integrating this function with respect to z, and with respect to z this t naught is a constant, so I will put this e power minus st naught outside of the integration, and this will become Laplace transform of x of t minus t naught will be equal to, I will put e power minus st naught outside of the integration. This integration is from minus infinite to plus infinite x of z e power minus sz e power minus sz dz, and this is the Laplace transform of the given signal xt, but there is a change in the variable in place of t, the variable is z here. So it does not make any difference. This will become the Laplace transform of x of t, which is x of s. So I can write the Laplace transform of x of t minus t naught will be equal to e minus st naught into x of s. It means that the time shifting property states that if we are shifting the signal by t naught unit in the time domain, then the signal in the s domain will be multiplied by this quantity e power minus st naught. Means if the Laplace transform of xt is known to us, then we can find the Laplace transform of x of t minus t naught without any calculation. We have to just multiply the signal in s domain with e power minus s into t naught, and this is what the property, time shifting property of the Laplace transform states. The next property is time scaling property. The next property is time scaling property. Time scaling property. Time scaling property of the Laplace transform states that if the Laplace transform of x of t is x of s, then Laplace transform of x of at will be equal to 1 by mod of a x of s by t. This is what the time scaling property states that if the variable t in the time, if the variable t is multiplied by a scalar quantity a, then the s domain of the signal will be divided by a, and also the variable s will also be divided by the same factor a. This is what the time scaling property states. Now we will discuss the proof. We know that the Laplace transform of x of at can be calculated by using relation x of at e power minus st. Now consider at is equal to some other variable, suppose it is z again. It means that t will be equal to z by a, and limit on the z will remain as it is, as it was on the t, because when t will become minus infinite, z will also become minus infinite, and when t will become plus infinite, z will also become plus infinite. So there is no change in the limit, but the variable t will become equal to z by a, and also from here dt will also be equal to dz upon a. So from here I will write it as Laplace transform of x of at will be equal to integration from minus infinite to plus infinite x of z into e power minus s into z by a into dz by a. So we can simply write it as this is the Laplace transform of the function. This is the Laplace transform of the function s by a, because this can be written as one part. I will write this 1 by a put outside of the integration minus infinite to plus infinite x of z e power minus s of minus s into z by a into dz, and it means that this is the Laplace transform of, because x of a is equal to x of a, x of s is equal to minus infinite e power minus st dt. It means that when I will find the value of x of s by a, this will be equal to minus infinite to plus infinite xt, and in place of s I will write here now in this relation s by a. So this will become e power minus s into t by a dt. Same relation is here. It means that this is the Laplace transform of this can be written in the form of x of s by a. So this will become 1 by a into x of s by a. This is the time scaling property of the Laplace transform. Now there is another property called time reversal property of the Laplace transform. This time reversal property it states that if the Laplace transform of xt is x of s, then Laplace transform of x of minus t, Laplace transform of x of minus t will be equal to x of minus s, and the we can find the proof as we know the Laplace transform of xt is equal to integration from minus infinite to plus infinite x of t into e power minus st dt. Then what will be the Laplace transform of x of minus t? This will be equal to minus infinite to plus infinite x of minus t e power minus st dt. Now replace the variable t with another variable minus p. Then this will become, here I will put in place of t I will put minus p, so this will become Laplace transform of x of minus t will be equal to, limit will remain same as limit is on t, the same limit will remain on the p. This will become x of p e power plus st dp, because if t is equal to p, then this will become dt will become equal to minus dp, and this x of t will become x of minus t will be equal to x of p, and when I will replace this t by minus p, this will become e power plus t into s, and this can be written as minus infinite to plus infinite x of p e power minus s minus p dt. In place of p, in place of t here it is the standard form. In the standard form, Laplace transform can be written as xt e power minus st dt. But instead of minus st here, it is equal to minus s into minus p. Means in place of variable t here it is minus p. So if the xs is written as in this form x of s, then this will be the Laplace transform of as x of minus s, because in place of t here it is minus s into minus p. So in place of t here it is minus t, and or we can say it in another way that in place of s here it is minus s. So if in place of s it is minus s, so this will become x of minus s. This is what the time reversal property of the Laplace transform states, that if we take the time reversal of the signal in time domain, then in the frequency, or we can say that in the s domain, the variable s will also be replaced by minus s. means the signal in the S domain will also be get reversed about the y axis. So this is all about this lecture. In the next lecture we will discuss some more important properties of the Laplace transform, and also we will go through the examples based on these properties. So this is all for today.